introduction. I will present the results and the methodology of our study on the usage of craft query languages in open source GitHub projects. And as a motivation, we probably all know that graph databases are kind of an interesting trend right now, and they're used in knowledge graphs, for example, like large open knowledge graphs such as Wikidata, but of course also in any kind of big data context at various companies. But what we're interested in is a more general usage of these technologies in open source projects, and we look at this from the perspective of craft query languages. So the first question then is, of course, which languages are interesting to look at? And we selected languages by the union of a number of criteria. We looked at languages indexed by GitHub's linguist framework, which classifies languages on GitHub and language artifacts on GitHub. And we also looked at recent related work related to craft query languages, technologies, and databases. From this resulting list, we then excluded languages which are either recent research developments, for example, G-Core, since there's no stable implementation of such languages. And we also excluded any language which is exclusive to a proprietary graph database, since there we don't expect any reliable or representative results on GitHub in open source repositories. And on a side note, there were also no actual repositories related to these languages. So the languages we selected for in total are Sparkle, which is a W3C recommendation for RDF graphs. Here's a simple example for a query selecting a nose edge between two persons. And I will show you the same example for all languages, just to give you an idea how they look like. The second language we looked at was Cypher, which is a query language for property graphs. Was initially introduced in the Neo4j project, but has since also been published in open standard in OpenCypher. And it uses a kind of ASCII art syntax for edge selection. The third language is Gremlin, which is a craft traversal language, part of the Apache Tinkerpop framework. And again, here is the example. And finally, GraphQL, which was initially developed as a replacement for the REST architecture. But since then, there have also been efforts to use it as a more general query language. And it uses a JSON-like syntax. So with these, in addition to these four languages, we also included, we also included two other languages as a baseline for comparison, which is Xquery, another W3C recommendation for querying documents, XML or JSON, and other document types, and of course SQL. Okay, so with these languages, we then had two research questions, which I will present today. The first question is in regards to the overall popularity of these languages in terms of the number of projects and the development of number of projects over time. Then popularity in terms of GitHub popularity metrics, such as stars. And finally, related to activities related to queries, meaning commits that deal with queries in source code. Secondly, we focus in on Sparkle specifically, and here we will distinguish between concrete and meta use cases of the language, which I will explain later, and also then look at the application domains and common usage and ontology kinds for data conceptualization used in such concrete applications. But first, let's start with the language popularity. And here our methodology has 4 steps. Before we could select projects, we have to introduce an intermediate step, since not all these languages are in any way tagged or recognized at GitHub. So we introduced a step to first select dependencies related to the languages, to then select projects based on these dependencies. In order to select dependencies, we use the Maven repository search engine, which indexes Maven repositories, including Maven Central, and obtain group and artifact IDs for any related dependency. Here are a few numbers of dependencies obtained, and we can see that GraphQL has the most dependencies. And another interesting point that the per group average, so the number of specific chars per project, is highest for Cypher, And when we look at these dependencies, we can see that Cypher is quite closely tied to the Neo4j project, which first introduced it. We also did this for the baseline. For xQuery, we have fewer dependencies, and of course, for SQL, a higher number. However, we modified the SQL baseline a little bit, since the base situation is slightly different here, since there's this connectors API, which is part of Java, so the language is not, so SQL is not, it doesn't behave in the same framework-like way that the other query languages do in terms of dependencies. And on top of this, these connector implementations for the most popular databases, according to DB engines, are not actually available via Maven. Therefore, we restrict our baseline just to the MySQL connector implementation, use this as a kind of consistent baseline, and from this we can see then how it compares to SQL in general. With these dependencies, we then select projects on GitHub using the GitHub's code search API on build files. So for example, for Maven, we would search all POM.xml files on GitHub to retrieve projects which use these dependencies and therefore are related to the query languages. With this approach, we get our first set of projects, which are about 10,000 for Cypher, and then Sparkle, GraphQL, and Gremlin in last place. In this figure, you can see the overlap between language usage in these repositories, which is not due to overlap in the actual dependencies, but overlap here actually means that any project in an overlapping part of the Venn diagram is related to all languages using different dependencies related to these languages. And an interesting note here is that Gremlin uses about a third of Gremlin projects actually uses more than one or more than one additional dependency, mostly Cypher, which, looking at the frameworks, is due to various libraries providing access for Cypher on top of Gremlin and the other way around. In this figure, you can see the development over time for project count, also including now the xQuery baseline in red. And here we see that xQuery and Sparkle developed quite similarly, with Sparkle being a little bit ahead. And around 2016, Cypher grew quite significantly. And if we include some important dates here, you can see that this correlates with the release of the OpenCypher language standard. And also GraphQL, we can see grows quite a lot recently, since it has been introduced only quite recently. Now, to show the MySQL baseline, we have to change the axis to a log scale, and can see that yes, more than one order of magnitude in difference between even Cypher and only the MySQL connector. Before getting to the activity analysis, we also have some additional filters, starting with the stars or stargazers, as I mentioned in the beginning, as a metric for popularity of projects. And here you can see the projects with 0, 1, or 2 or more stars in dark. And given the overall number of projects and the significant reduction, we then consider these projects as popular in our activity analysis, which excludes at least projects without any stars and projects, single developer projects with only a self-star. In terms of reduction in the total number, this looks something like this. Or we can now see that there are more popular Sparkle projects, closely followed by Cypher, and there's quite a significant drop down to GraphQL and Gremlin. So for the activity analysis, we will focus on Sparkle and Cypher. In addition to popularity, we also, for finding commits that deal with queries, have to identify queries in source code. And this is not entirely straightforward, since these query frameworks don't use any standardized method of including queries. So the only thing we basically know is that they're somehow embedded in a string or in a dedicated file. And for such strings, there can, of course, be a range of composition techniques used in Java, like concatenation or streams, etc. And there might also be some arguments which are included. Like in this example here, there's a prefix definition for the Sparkle prefixes included as a variable. So in order to locate queries, we use a heuristic based on the language grammars, and specifically we try to match query headers, since each query has to have one header, and there's a low impact of any argument splicing, etc., in the query headers, and we estimated that this is quite accurate in detecting the queries in the source code. So with this, we can look at the activity of repositories. And first, here again, the complete definition of a query activity. We consider a query activity to be a commit that changes a Java method, which is our level of granularity, that contains a query in its source code, or a commit that changes a dedicated query file, which is either a Sparkle or a Q file for Sparkle, or a Cypher or Cypher file for Cypher. With these activities, we can then look at the temporal evolution of activity of projects by looking at either unique repositories, unique developers, or unique artifacts. This looks like this. So this is the activity related to unique repositories, where the solid lines represent queries in Java methods, and the dotted lines represent queries in dedicated files. Each data point is an accumulation of 120 days. We have a sliding window across time to produce this activity. And what we can see here is, first of all, that there's more activity related to Sparkle. But Cypher actually is almost on the same level of activity in 2018, even though it got released and became popular later, so it grew a lot faster. It might surpass Sparkle in the future, but we can also observe some stagnation in growth around 2018, so it's not certain that it will. In addition, for the dedicated query files, we can see that Cypher dedicated files are very rarely used, and also Sparkle dedicated files are far less common than method included queries, even though it's slightly more than for Cypher. When we also include the popularity criterion, so only look at projects with 2 or more stars now, we can see pretty much the same picture, and Sparkle is even more popular and more active in this comparison. And the full activities for unique developers and unique artifacts show similar results, and you can look at them in the full paper. So secondly, we will look at the concrete usage of Sparkle. And here we again start with the same set of Sparkle projects we initially selected, and we will then use additional filters to reduce the number of projects, so that we can then manually look at them based on a ranking we define. So this looks like this. We use the Sparkle projects we initially selected. We filter by the number of stars, and then we also introduce some additional filters. We select only projects with any queries in the source code using the previous defined heuristic. And we also require those queries to be included in relevant files, by which we mean that we exclude test cases and other indicators of the query not actually being part of the project, but just of testing of, for example, a library or framework. We also introduce some additional popularity filters, such as the project must have at least one fork, and a recency requirement, so we require a push within the last year. For these more strictly filtered projects, we then rank them by the number of relevant queries included, the distribution of those queries across the project, and the existence of a love URI, which is a collection of vocabularies that might be used in Sparkle queries, so another indication of actual Sparkle usage. Based on this filtered list, we then manually label the top 50% of projects using the following categories. So first, we have the concrete category, which means that it's an application that uses concrete instance data. One example from the data set is a museum management system. We then distinguish this from projects which only use Sparkle in a meta way, by which we mean that the applications simply query for the graph structure, so they only include very simple Sparkle queries that return general graphs. So for example, a database exploration tool which just renders any arbitrary graph would be such a meta application. And then finally, we label everything else as irrelevant, and this includes things like libraries or frameworks, and also other uses of Sparkle, for example, for the purpose of reasoning, or as you can see here, a Sparkle to a SQL compiler. With this, we find 12 concrete applications in this high-ranking data set, and then 21 meta applications and 42 irrelevant applications. And we will look at these 12 applications in more detail in terms of the domains and ontologies. So looking at these 12 applications, we can see that about half of them are related to some management task, 3 to document management, for example, the museum example I mentioned, and we also have some library system. Another 3 are related to process management, and then of the remaining applications, 4 are data visualization tasks, and then 2 other applications, like a web application framework, which itself uses Sparkle. For ontology existence, we categorize ontologies in 3 categories. And I will explain them using this example of the Oslo Public Library that I mentioned before. Here so the 3 categories we look at are first project-specific ontologies, that is ontologies designed specifically for this project. And such an ontology is used, for example, in the Oslo Public Library system, which specifies specific data types for this library. And we can see that most projects actually use project-specific ontologies. On top of that, it is common to define ontologies and reuse them across multiple applications. So the second group here are domain-specific ontologies. And the library example here uses the Dublin Core Metadata Initiative ontology, which is used for tagging metadata in various applications. And we can also see that all of the 12 applications use at least one or commonly multiple of such ontologies. And finally, as we would have expected, generic vocabularies are used as well. For example, RDF schema is quite frequently used in all of these projects. Okay, so with this, as a conclusion, we observed that Sparkle and Cypher are the most frequent graph-related query languages, but they are significantly less frequent than MySQL, and therefore also SQL in general. We observed that there are more popular Sparkle projects and that they are currently more active and have been in the past. This might or might not continue in the future. And we also observed that there are only a few Sparkle applications that actually work on concrete data and are also popular, but they do commonly use a number of different diverse ontologies. Yeah, so thank you for your attention, and our data sets are available online. We did not yet look at bug fixes. We might look at something like this in the future. So currently, I can't give you any precise insights there. But it's certainly something you can do with this data set. And
questions. What other research questions? What are other uses you can do with this data that you've collected?
So some things. I mean, you mentioned bug fixes. That's something that's interesting, and also looking at how precisely the queries are constructed. In addition, it will also be interesting to compare the string-embedded queries, for example, to something like a fluid API, or look at how users construct such APIs manually, which we might have not detected as queries. So that's something we could do.
I'll ask my other question. So you've looked at GitHub, right?
Yep.
You've got all your data from GitHub, and you've only looked at projects that are Java-based.
Yes.
Do you think you would have got different results if you used a different source and different criteria for programming language selection?
Possibly, yes. I mean, for example, GraphQL would be, we suspect, significantly more popular in Java script applications, for example, since it's used for web APIs. But yeah, we restricted to Java in this study, mainly because the other languages are very popular there. Of course, different source. If we would have looked at not only open source projects, but also industrial projects, there might be a completely different picture there. Also with the proprietary databases, for example.
Maybe looking at GitLab also. And my last question is the concrete applications. You looked at only Sparkle.
Yes.
Why?
I mean, Sparkle was the most popular language, most frequently occurring, so we focus on this for now. We're also interested, of course, in looking at the other applications. And also for Sparkle, there are, I think, more interesting distinctions between the use cases, since it can also be used for reasoning applications, and it uses ontologies. So